Okay, so now in the last unit that we have defined what it means to be an exponential equation or an exponential function, we know that we're dealing with equations that have this form of a times b to the x. Okay, and that's our basic structure for the exponential family. And so we're going to start looking at this as more of a function and less of a sequence. So we have we're going to start the conversations with this exponential equation. And so today we'll be investigating what happens when we change the equations of an exponential functions. And so if you are in class live, you'll be going to a Desmos, and graphing this. But on video, we'll just kind of step you through it. Okay, so it says, where does the graph cross the y-axis? What values does a function choose? What y values does a function use? X and y values. Okay, so we just need to make some basic observations. So when we graph this in, well, actually, what I could do is I can graph this in Graph and Calc. So if I go up to y equals and clear out all this, I can put in 5 to the x power, and I can graph it. And so the graph looks like this. So if we notice, maybe we can split the screen here, get back to our notes. If you notice about these questions here, so here is that y equals 5 to the x. There we go. And it crosses the y-axis at 0, 1. So, whoops. At 0, 1, that's the y-intercept. And it says, what values of x does the function use? So if we zoom out on this function here, we can see that, first of all, the y values get really big very quickly. If we look at the positive y-axis going up, and they get really small, they get really close to 0 as we go into the negative values, and but it doesn't go negative at all. It just gets closer and closer to the x-axis. So our values of x is that we use all reals from left to right. Our values of y is that we use y values that are greater than 0. So they're all positive. In other words, the x-axis is an asymptote. Let me see, I've written that kind of into the graph, so let me slide all that over. There we go. And so let's get a couple of points here. We've got 0, 1, so that is probably about here. And then let's see, at 1 we go up to 5, right? Because 5 to the first power is 5. And at 2, I'd have to shrink this down a little bit. But at 2, you can see on the graph, at 2 we cross 25 because 5 to the second power is 25. 5 squared is 25. So we have those questions as we go into the first quadrant, and as we go into the second quadrant, you can see how it gets closer and closer to 0. If we really spread this out here, we can kind of see that it gets closer and closer and closer and closer to 0, but never quite touches 0. So all of these represent negative powers. And so what we basically have is we end up having this curve that, trying to sketch it in here, that gets very large in y values very quickly, and then goes beneath 1 to fractional values, and then eventually gets closer and closer to that horizontal axis. So, so the question is, do you think it'll ever touch the axis? We talked about that above. No. The x-axis represents y equals 0. And so when we look at the expression 5 to the x power equals 0, there is no value for x. that makes y 0. So that's why it's asymptotic. So let's talk a little bit then. I don't think we need our calculator anymore. Let's talk a little bit about what happens over here. And I might not have drawn this too accurately. Actually, now that I look at this, I want to kind of redraw this because it gets closer to the x-axis faster than what I drew. So it's probably more like, whoops, more like this. There we go. And then it probably dips real close here like that. And so this point represents 5 to the minus 1 power. And if you remember, negative powers just means that we would move that 5 to the denominator. So it means 1/5. And then this one here would be 5 to the negative 2 power. And that just means 1 over 5 to the positive 2 power, which means 1 over 25. So if you remember your negative powers, that's what's happening there. So that's 1/25. So we're getting really close to the horizontal axis, but we're never going to 0. And so that's what happens when you continue to have these negative powers here. Let me make that a little more obvious that it's a negative 2. There we go. Okay, so let's take a look at what is happening here. And we did this a little earlier, where we would modify our functions and see how they change on the axis. So we're gonna look at a couple of different functions here. So let's first take a look at y equals 2 to the x. So remember, these are all basically these exponentials, a times b to the x, right? And so in all of these instances, we have an a value that equals 1. In other words, that's our start value, right? And if you notice, our start value is that intercept. So they all have an intercept of 1. And then the b, we call b the base, technically speaking. That's why we label it b. B is the base, and so we have varying bases. For this first graph, we have a base equal to 2, and this base is equal to 3, and this base is equal to a half. And actually, looking at that last one, it's a little bit ambiguous, but I am reasonably sure that this whole fraction is to the power x, not just the 1, not just the numerator, but that whole fraction. Okay, so let's talk about that first one, base 2 to the x. So, you know, if we look at this, we've got -4 to +4, right? I'm just going to make a little table underneath here of x values. And I'm going to have -4 and -2 and 0 and 2 and 4. I'm going to pare it down a little bit. And then we're going to look at our 3 functions. Let's make a little bit table here. So that first function is y equals 2 to the x. So we know 2 to the 0 is 1, right? That's our start value. So that is right here. And then 2 squared equals 4. Excuse me. Yeah, 2 squared equals 4. So 2 squared equals 4. That's here. And 2 to the 4th is 2 times 2 is 4 times 2 is 8 times 2 is 16. And that's off the graph. Okay, so in retrospect, maybe 1 and 3 might not be bad to insert here. So 2 to the 1 equals 2. 2 to the 1 equals 2. Let me get my blue pen back out again. 2 to the 1 equals 2. And 2 cubed equals 8. I think 8 is still on the graph, so that helps me. 2 cubed is 8. Okay, let's take a look at negative values. So 2 to the, I'm going to put these other values in here, -1 and -3. I guess I shouldn't have tried to cut corners. So let's get rid of that. 2 to the -1 is 1 over 2 to the first power, so it's a half. So this one is, to the -1, we'd be at a half. And then 2 to the -2, 2 to the -2 would be 1 over 2 squared, which is 1 over 4. So 1 over 2, that's 1 over 4. That's even closer. And then 2 to the -3, 2 to the -3 is 1 over 2 cubed, which is 1 over 8. So that's even closer, right? It's getting so close that we're almost mistaking it for touching the axis when it really doesn't, because we're getting that close. And so 2 to the x looks like this. Let's try to see if I can draw that a little more accurately. That's good enough. Okay, so that's 2 to the x. So y-intercept is at 1, so 0, 1. The domain, the x values are all reals. The range are all positives, right? It's greater than 0. And the asymptote is that horizontal axis, which is y equals 0. And so let's look at a base 3. Let's look at changing the base. So we're going to look at a base 3. So we have y equals 3 to the x. And actually what I'm going to do, I think, is I'm going to get rid of the -4 and the +4. That'd probably be a better idea. Okay, so let's start back at 0, though. 3 to the 0 equals 1. We're at that same intercept. And that goes back to that standard a times b to the x form, because we know that a value, that's our start value, is at 1 for sequences, because sequences are positive, basically. So we're starting at that positive value 1. Okay, so 3 to the first power is 3. 3 to the second power is 9, right? 3 times 3. 3 to the third power, 3 times 3 times 3 is 27. So we would go up to 3 and then go up to 9. And obviously we can't graph 27 because it's off the grid. So looking at the negatives then, 3 to the -1 is 1/3, right? That negative power is just saying put it in the denominator. 3 to the -2 is 1 over 3 squared, which is 1 over 9. And 3 to the -3 is 1 over 3 to the +3, 3 cubed, which is 1 over 27. So we have 1/3 and 1/9. So 1/3 is probably, it's just under a half, right? 1/9 is probably, right, just squeeze it in there. 1/27, oof. It almost looks like it's on the line, but it's just a little bit off the line. And so we have this, and notice as I'm drawing it, it's going to cross over the blue one and get tighter as it goes. Let me do that again. So it's going to come down, cross over the blue one at the intercept, and then it's going to be tighter to that horizontal axis than the blue one is. And I'm having a hard time showing it tighter. So I'm going to draw it one more time. So it's above the blue, and then it's going to cross over and go under the blue because it's going to be tighter to the horizontal axis. That's a little bit better. Okay, so that is, so we're changing the base. We're upping the base, and we get that crossing at the intercept. Obviously 3 to a power is going to grow faster, so it's going to get more vertical as we go off on the right. And it's, since all of them are fractions on the left, it's going to get tighter on the left. So we still have the same intercept. We're still using all real numbers for the x. The y values are still positive, and our asymptote is still 0. So let's take a look at a half. Okay, so a half to the 0 power is still 1. So we're still starting at that same location. And a half to the first power is a half. So notice the fractions now are going to the right. So when we have positive power, since our base is a fraction between 0 and 1, now these values are starting to decrease as we go to the right. A half squared is a half times a half, which is a fourth. So then we're right about there. And a half cubed, half times a half times a half, is an eighth. And so what we're literally seeing is we're seeing, if you notice, I'll highlight them in green because we have 1 and a half and a quarter and an eighth. And that was these values in the negatives. But now we have the reciprocal of the base, right? We have y equals a half to the x. So now we have the reciprocal of the base. And so now we've basically swapped our fractions and our whole numbers. So if we go into the negative powers, a half to the minus 1 power means the 2 and the 1 need to swap locations, and 2 over 1 to the first power is just 2. And a half to the minus 2 power means we just flip it because it's negative power. 2 over 1 is 2, and 2 squared is 4. So for the negative 1 power, we're now up here at 2. And for the negative 2 power, we're now up here at 4. And for that negative 3 power, we would be at 8. And so if you notice, it is a reflection of the blue still crossing here, but it's a reflection of the blue function over the y-axis. So we still have the same intercept at 0, 1. We're still using all reals. We're still in the first and second quadrant, so positive y values. So nothing else changes. You know, all these charts on the bottom are all the same. Same intercept, same domain, same range, same asymptote. So we're just talking about really that basis determining how fast this function grows as we move into the positive x values. So that the table literally stays the same. So that's probably the best comment we have, is that doesn't affect the table. So changing the base doesn't affect table. Above, that one, above, does affect growth. So that's that table. Okay, so as we're going through here, we're looking at, it says on the plane below, graph the 3 following functions, each one in a different color. Pen or pencil, complete the table below. So we're starting out with the 2 to the x again. So let me just, this is our base of 2, right? And again, we are looking at, in fact, we're looking at it really closely now. We're looking at this form of the start value times the base to a power, right? And now we actually have start values here that are other than 1, because they were all, like I mentioned up here, they were all 1. Now they're different values. So here, this is what we had originally. And so my A equals 1, that's my start, that's my intercept. And my B, my base, is 2. So we're going to graph that one. And this is counting by 2s. So don't be fooled, right? If we're counting by 2s here, then the intercept 0, 1 is right here. And then this is 2 to the first power would be here, 2 to the second power would be here, 2 to the third power would be here, 2 to the half would be here, and 2 to the minus 2 or squared would be there. So that is a little different look, but it's because of the scale. So that is, put it up here, y equals 2 to the x. Okay, so there's y equals 2 to the x. All right, so now we want y equals 3 times 2 to the x. So if you notice, we're changing the a. So let's go green. So now our start value is 3, and our base is still 2. Okay, so let's fill in this table, I guess, before we move too far with the intercept is 0, 1. The domain is still all reals. The ranges are still all positive y values. Asymptote is still at y equals 0. Now let's graph 3 times 2 to the x. So, you know, I think a really useful thing would be maybe to cut down on the math, maybe put them in here. So let's go back to our y equals. I need 2 to the x, 2 to the x, and I'm going to make that blue because I am working in blue. There we go. Okay, and then the next one is going to be 3 times 2 to the x. Whoops, I forgot to hit the caret. 2 to the x. There we go. And that should be a times, not a plus. Times. There we go. 3 times 2 to the x. I want to make that green. So here is 3 times 2 to the x. So notice when I have 3 times 2 to the x, my intercept is 0, 3. Notice the shape is the same though, right? It's still exponential. So what that means is all of these things don't change. We still have that shape. Okay, but our intercept changed. Our intercept is now up at 3. So it's now up here at 3. And let's see, when x equals 1, y equals right there, right? When x equals 1, see if I can get it exactly, y equals 6. So think about that. That's 3 times 2, right? 3 times 2 to the first power. And then when x equals 2, y equals 12. I can't get, there you go. So that is right, when x equals 2, y equals 12. That's right there. It's 3 times 2 squared. And then when x is equal to -1, when x is equal to -1, y is equal to 1.5. Because -1 means 2 to the -1 power, which is a half. So we're at 1.5. And then if we go out here, we're at 0.75. So we're about right there. And so we have something that grows faster, and it's kind of like the zombies, right? It's kind of like if we had we started with 1 zombie and they bit somebody each day or each week. Now we're starting with 3 zombies, right? When we start more, it just bumps up all of those values universally across the table, and so across the graph too. So it's like we're starting with 3 zombies, right? And they're biting somebody every week. So, and then the last one, I can't really use the zombie reference because you don't really want to start with half a zombie. I'm not sure what you get. But now our A is a half, and our base is still 2. So you can probably speculate what this intercept is. So take a moment to think about that at 0, what. So as you're thinking about that, I'm going to go ahead and graph it. So I'm going to come down here and I'm going to do 1/2, 1 divided by 2, and I put that in brackets. Whoops, that's not a 2. And then times 2 caret x. And I'm going to make that orange because I'm using an orange pen. Okay. And so when I graph that, there's that last function, so you can see that that intercept is a half, right? That's our start value. That's what our A is. It's a half. So it's right here. So it just cut everything in half, which means when x equals 1, we're at half the base, which is 1. And then when x equals 2, we're up here at 2. So it's half of 2 squared, which is half of 4, which is 2. And then when we're at 3, it's half of 2 cubed, right? So 2 cubed is 8, and half of that is 4. And then this just gets super tiny, super fast. At -1, we're at down here at a quarter already. It's half of a half, right? And so this is just getting tighter and tighter with the axis, as exponentials do. That's that asymptotic behavior. So it looks like this. If I can squeeze it in there. And so that is y equals 1/2 times 2 to the x power. I'll write it like that. But that's like, because we're changing that a value, that start value, that's the only thing that's changing. Everything else in the table, it's still the same shape, and it's still the same 2 quadrants in the coordinate plane. So that is all still the same. Okay, so when we change the a value, it is changing that that start value, and it's scaling everything. Okay, so that's our scale factor. Okay, so what do you notice? We're changing a. So when we change that a value, that is our scale factor. I think I used that word in the previous unit when we were graphing. That's our scale factor. It's scaling everything by that a value. When a is 3, everything tripled. When a is a half, everything got cut in half compared to that blue function. We could almost call that blue function our parent function. Okay, so let's see what happens when we start adding things instead of multiplying by things. So this is something that this is something new. So let's go back to y equals, and we're going to get rid of this, and we're going to keep our parent function. And we're going to look at these 3 functions. So I'm going to keep that parent function, and I'm going to look at 2x plus 1. So let's change some colors here. I'll choose red, and I'll choose green, and I'll choose purple. There we go. Red and green and purple. So red, I'm going to put 2 to the x, 2 to the x, and then I got to get out of the power, because the plus 1 is not in the power, it's added on to the end. And so when I graph that, notice it took that curve and it just scooted it up by 1. And if you notice, everything is 1 bigger than it was. We were down here at 0, 1, now we're at 0, 2. When x is equal to 1, we were at 2, now we're at 3. When x is equal to 2, we were at 4, now we're at 5. Okay, so the y-intercept changed. So what is this? This is red. So this is a shift up 1. So now we're at 0, 2. But you know what? We still have the same shape, and we're still in the same location on the coordinate plane, and we still have the same asymptote. So that is going to look like, instead of going at 1, we're going to shift it up 1 to 2. So we're going to take that parent function. So actually, if I do this, right, this is that parent function. I'm drawing it in gray, so it's kind of not a focal point, if that makes sense. So it looks, that parent function looks something like, whoops. So that was blue up above. So it looks something like that. And now what we're going to do is we're going to take that parent function and we're going to bump it up here. Okay, and I'm going to change it to red. So now we're at 0, 2, red pen. There we go. We're at 0, 2 for the intercept. This is now 1, 3, right? This is now 2, 5, because we're adding 1, right? We're taking it 2, squaring it, that's 4, plus 1 is 5. So we're shifting that 1 up 1. So you could probably speculate then. Let's see, what's the next color I'm using? The next color is green. Okay, so you can speculate then what this is doing. That is going to be shift down 3. And so if we take the parent function and shift it down 3, let's take a look at that one. So this is 2 caret x, get out of the power, subtract 3. And let's take a look at what that looks like on the graph. So we can see that compared to the parent function, the blue, actually, you know what I should do? I should go back up to that parent function and make it gray. That would be actually really be good. There we go. That's pretty grayish. That way it's kind of matching my notability file. So if you notice, the parent function was right there at 0, 1, and it moved down 1, 2, 3, right, to down here, -2. That's down 3 below where it was. So if I take this function, in fact, I'm going to take this whole, let me take this whole thing. I'm going to try to grab the arrow at the top too. And I duplicate it, and I slide it down. See, notice I took the points with it. I slide it down 1, 2, 3. Then it's right there. And let me style it green. And so now I'm at 0, -2 for the intercept. So 0, -2 for the intercept instead of the parent function, which is 0, 1. Maybe I should label these. And then this was the shift up 1. So this is 0, 2. So now I'm at, I shifted it down. So when I shift it down, we have to remember that everything is sliding down, including that asymptote. So that asymptote now slid down 3 as well. So that asymptote is now at y equals -3. And which means I'm using all of the y values that are greater than -3. From left to right, though, my domain, I'm still using all the numbers. Okay, and then this last one, so this last one is, we've got a -1 up in the power. So that's different, right? It's up in the power. It's up here. Okay, so what does that do? So let's go to that purple one. So it's 2 to the power x, and I'm going to stay up in the power. I'm going to put -1 in the power. So how is that compared to the parent function? So we look at that, and we see, there it is, that purple one. So the question is where's this intercept now? We know the parent function's intercept is 0, 1. Where are we at a value of 1? And we're at a value of 1 right there. Okay, so that -1 shifted it to the right 1. So shift right 1. So just like what was happening in our previous unit, if we would take, let me try again to kind of lasso all of this. I'm going to lasso all of this, and I'm going to duplicate it, and I'm going to take this, right, it's right here, and I'm going to shift it over 1. So I'm sliding it to the right 1. Right there. And then let's color that purple. Okay, so now it's there, and now what happened is this point here on the gray slid to here on the purple. And if you remember that this is a half, so this intercept here is now 0, a half is the intercept. So it's now 0, a half. Okay, so how do we figure out it's a 0, comma a half? Well, if we look up here, and we can see that we have 2 to the x and 2 to the minus 1. And so here is my intercept, okay, because that makes a power of x minus 1. From left to right, we still use all the reals. We're sliding left to right, not up and down. So we're still with the parent function with the asymptote at y equals 0, and we're still using the quadrants 1 and 2. We're still that has positive numbers for the range. So in general, what we're looking at, and this is kind of the meat and potatoes here, is that we can write a general function just like, oh, let me use a different color. Let me use, what haven't I used on this page? Gosh, I've used it all, really. Pink, I guess. So we are generalizing, and these A's and B's and H's and K's should start to look familiar, right? We're starting to do things like shift up or down, right? We're starting to do things like shift or slide left and right. So we're starting to do those things, and we're starting to set up that general expression. And so we have one for exponentials too. This is just going to add to the, the absolute values and the square roots and the squares that we did in a previous unit. So we have this general expression here, and where we have the y-intercept. This is the y-intercept. And we have a horizontal, horizontal slide. So we have, when h is positive, how about writing it like this? Then it goes right, and when h is negative, we'll see a plus sign in there. It'll go left. And then this is our vertical shift. And when k is positive, we go up. And when k is negative, we go down. All of that stuff. So we're starting to fall into that pattern, is basically what's happening here. So that's going to be our focal point then for this. Is to recognize and be able to identify and work with those transformations on exponentials. So learning target number 1 is the graph of the parent function. So let me call this maybe exponential parent. So the exponential parent was what I was graphing up here in gray, right? So the exponential parent on the coordinate plane looks like an intercept. I'll even graph it gray. An intercept at 1 and a curve that gets big on the right and then gets asymptotic on the left. And then we have along the axis here, we have an asymptote. So this is an asymptote, y equals 0, and an intercept 0, 1. So that's the parent function. That's the first thing. So we have this parent function. And then learning target number 2 was working with changing that base. So in general, we call that growth and decay. When we have this function y equals a times b to the x, I'm just going to write it in real simple form. We're talking about looking at b. So if b is greater than 1, we have growth, which means it looks like We have our intercept, we'll just say it's at 0, 1. It looks like that. And when b is between 0 and 1, we have decay. That means it's a fraction, like a half or a third. So we have something that, we have the swapping of the y values. So we have something that looks like big on the left, little on the right. So it looks like that. And then the last learning target is the full transformation. And so that is, I'm just going to pull that from above here. It's the, let me just write it as y equals a times b to the x minus h in the power plus k. That's not in the power. And then we have our, go pink. This is our y-intercept. I'm just taking the wording from up here. This is our horizontal shift. This is our vertical shift. And B is our and then B is our base. So that's going to be determining if we have a growth or a decay. So, and then I'll just add the, when H is positive, we go right. And when H is positive, that means this negative is here, right? Because positive H would be X minus a positive number. And when H is negative, then it would be X minus a negative, and the plus would show up here. Remember that from the previous unit? So when H is negative, then we go left, but we actually see a positive up in that equation. That's that whole opposite same thing I was reinforcing before. K is positive, we shift up. And if K is negative, we shift down. Okay, so again, I've supplied some answers for the check your understanding so that you can check that as you go without getting into Blackboard. But then what you should do is work on that check your understanding and then check that against the notes in Blackboard for this section. And then the practice worksheet is actually graphing exponentials. So graphing them point by point, and then commenting on growth and decay at the end.